So for this problem, we have our same blue bolt stuck through a couple pieces of metal, and we're pulling the pieces of metal apart, same as before. However, this time, we still have a 1,000-pound force pulling to the right, but now we have two 500-pound forces pulling to the left. And then the question asks us to find the maximum shear stress acting on the bolt. So the first thing we can do right away is we talked in the last example about how shear stress tau is equal to force over area, and the area is going to be the area that's parallel to that force. So the area is going to be the same as it was in the previous problem, that 0.0491 inches squared. So that's one of the things we need right away. So the next thing we need to figure out is what force are we supposed to use to calculate the shear stress? Because on one hand, we have 1,000 pounds pulling to the right and a total of 1,000 pounds pulling to the left, which is the same as the previous problem. However, this time that force is broken up into a 500-pound increment and then a second 500-pound increment. And we have to figure out if that changes the problem at all for our shear stress. And it turns out that it does, right? So when we had the previous problem, it looked like this. With the two pieces of metal being pulled, the bolt going through them, pulling to the left, pulling to the right. And if you imagined that pin snapping, right? So imagine we were able to just look at the pin and ignore the pieces of metal. You could imagine it breaking kind of like that, where you pulled with 1,000 pounds right here, and you pulled with 1,000 pounds right here, and then right in the middle you get that bend and snap, right? So that would be what we refer to as a shear failure. And if we look at that shear failure location, we can see that it's bounded by a 1,000-pound force on one side and a 1,000-pound force on the other. So that's why we used 1,000 pounds when we're calculating force for how it was going to break. So now let's look at the pin in this example. So since we have a top force of 500 pounds, a middle force of 1,000 pounds, and a bottom force of 500, just think about in real life what that pin would look like if you pulled harder and harder and harder in those directions. What you would end up with is something like this, where it would kind of bend out to one side from that top 500 pounds, and then it would get like a bend back towards the bottom with the other 500 pounds, right? So we've got our 1,000 pounds, our 500 pounds, and our other 500 pounds. So what that creates is, in the previous problem, we had one location where the pin was in danger of shearing. Now we have two locations where it's in danger of shearing. And if you look at how the forces are distributed on either side of those shear failure locations, you have a 500 pounds of force on top of the first one, and then this 1,000 pounds kind of breaks up to be 500 pounds pulling on one shear plane and 500 pounds pulling on the other shear plane. So what we end up with is that at each individual shear location, there's only 500 pounds of force acting to cause the pin to bend or break, right? So that's what makes this problem different. And if you have further questions, this is called the double shear pin problem. You can find it online. There's gonna be a YouTube video of a professional engineer explainer on YouTube walking through this as well, if you'd rather see a second opinion on how to go about determining that it's 500 pounds. But once we have that the force is 500 pounds, the problem becomes very simple. 500 pounds divided by 0.491 inches squared gives us a maximum shear stress of 10,186 psi.